Okay, so today we are very happy to have Ignacio Cirac, who is at the Max-Planck Institute for Quantum-Optics, and he will be telling us about quantum computing and the difficulty of simulating quantum many-body systems.
Thank you, Juan. So it's my great pleasure to be here and this colloquium and talk about quantum computing and applications in solving many-body problems. So I guess that you know well that many-body problems are difficult to solve with classical computers, and the difficulty lies in the the fact that the description of quantum mechanical systems is difficult with classical methods, and then there is a hope that quantum computers can do something and help. And I want to talk a little bit about that. So I want to start just making some general comments about the whole field of quantum simulation, all the expectations that people are putting, the different setups, how things are going. And then later on, I'll move on to explaining some of the basic quantum algorithms that are being used or planned for quantum computers and many-body systems. And at the end, I will talk about a couple of applications, so in particular, some that are not so well known, like in lattice gauge theories and quantum chemistry, but very briefly. Okay, so you know what a quantum computer is, and that's something that some of us have been working for a very long time now. For myself, in my case, it's more than 25 years, and we always hope to have a quantum computer would be allowed to deal with 1,000, 10,000 qubits, and to apply quantum gates to drive everything coherently, at the end perform measurements. And with that, we know that indeed we had something like that, this would be very useful. This would be very useful because we know quite a few applications where quantum computers can have an advantage with respect to classical computers. I mean, this is not what we have now. What we have is something else, are what so-called NISQ devices or analog quantum computers. So NISQ devices are quantum computers in the sense of what we think. However, they are small and they are noisy. So this means that whenever you perform some gate or you apply some gate, perform some unitary evolution between the qubits that compose the quantum computer, there is a probability of an error, and these errors accumulate. So in practice, this means that after few gates, then the solution of your problem or the state of your quantum computer would not be the ideal one. And for analog quantum computers, that's something that, of course, nobody thinks about analog classical computers nowadays, but many years ago, so people were using analog classical computers to solve certain problems, and they are available now, the quantum versions of that. And the idea there is what you do is that you don't have gates, you don't have a discretization of the dynamics, but rather you tune the parameters in one system that you can control relatively well. And by tuning the parameters, you can tailor what is the Hamiltonian of the particles that are in your system that is under control. And if you do it well, maybe you can solve some problems with that systems as well that you cannot solve with classical computers. So NISQ devices we have, there was a wonderful experiment by Google with 53 qubits in which they showed very clearly quantum advantage, namely they were able to solve one task that you cannot solve with classical computers as efficient as with this quantum computer. And with analog computers, and people have also done some simulations that are very hard to compute with classical computers. However, there is a big hope that these systems now are useful for something else. So you probably have read headlines of many newspapers in which people claim that now with these systems, we will be able to solve optimization problems, traffic problems, climate change, cancer, whatever. And there's a huge hype, a huge exaggeration, and we're very, very far from that. So we had the scalable quantum computers, the one that everybody wants to build. And I would tell you that, some of this would still be an exaggeration, but however, there would be some hope that something like that would work. However, with what we have in practice and what is planned, the fact that they have errors or the fact that they are analog makes that most of the applications that we know for quantum computers simply don't apply. So I want to talk about one that may apply. This is the simulation of many-body systems, and as you will see, this is a little bit special. But before that, I want to make some points that I want to argue a little bit before explaining things. So talking about quantum simulation, so the idea now is to use one of these NISQ devices or these analog quantum computers to solve many-body problems. And this is what is called quantum simulation. So you want to simulate a quantum system and quantum many-body systems with a quantum system. This is your quantum computer, your analog quantum computer. And so I want to claim that quantum simulation is probably the most suitable application of quantum computers, and especially from these first generations until we don't have one of these scalable quantum computers. So it's very suitable for that. Second point is that analog quantum computers at the moment are much better off for quantum simulation than digital quantum computers, and I want to explain why. The third point is, so why do we want quantum simulation? So what is the most relevant applications of quantum simulation? So people will tell you that this maybe solves some specific model like Hubbard models or some lattice gate theories or something like that. From my point of view, the most important application of quantum simulation is that will give us benchmarking. So we have now many methods to solve many-body problems, but many of them are uncontrolled. And so one needs to work together with systems that can be controllable in order to advance in these methods, these classical methods. And I will insist a little bit on that. And also another message that I want to convey is that still, I mean, these quantum simulations with analog quantum computers on analog or digital quantum computers is not yet here. And so there's a lot of effort. And I mean, hopefully in the next few years, we will see something, let's say, coming out that will have at least scientific interest. Okay, so these are problems that appear in physics and chemistry. You want to solve a molecule, meaning that somebody tells you, I have that many nuclei and that many electrons, and I would like to know what is the geometrical configuration in which I have equilibrium. That's a chemical problem. Or you have two molecules, and then you want to see whether they can react, and then they can have some product. We have problems in condensed matter physics where you have a solid composed of many particles or many atoms and then many electrons that can move. That's another many-body problems. And at low temperatures, at least, this behaves in a very quantum matter. Or in high energy physics, if you have quantum field theories and you discretize, well, and you want to solve this also quantum many-body problem. You can think that if you discretize a space, then you can have like a lattice, and in each lattice there is a quantum degree of freedom. So there are many quantum degrees of freedom. So it's again a quantum many-body problem. So all these problems have in common that they can be just rephrased in terms of a lattice model. So you have a chemical problem, then you can just consider orbitals, expand your field operators in these orbitals, and then you will have a discretization in terms of a lattice in which the Coulomb interaction between the electrons and nuclei and so on, they will give rise to some Hamiltonians in the lattice. So this can be rephrased as a lattice problem and a Hamiltonian. Also in material science, then you can, there is a natural discretization of your system because you have a periodic structure of the atoms. So at the end, typical models, phenomenological models of condensed matter physics are also written in terms of a lattice. Now, the difference is that typically the interactions are short range. So these particles that are in the lattice, the vertices of these lattices can interact only with the ones that are around them. And in high energy physics, you can also discretize space and put it on a lattice, and then the interaction will be very local because you have to conserve, you have to keep causality. So at the end, many-body problems, when you put it on a piece of paper and then you want to solve them with a computer, so typically what you have to solve is a lattice system where, without loss of generality, you can think that you have something like qubits in each of the lattice sides. Somebody gives you a Hamiltonian, and then you have to solve these Hamiltonians, meaning that if you're interested, for example, at zero temperature behavior, you will have to find the ground state. And once you have the ground state, you have to compute the physical properties that you're interested in. Or if you're interested in the dynamics, then you will have to evolve your system according to the dynamics generated by this Hamiltonian and so on. But in any case, if you want to solve this problem with a classical computer, so typically you will have to write one state, which should be a linear combination of all possible configurations that you can have your qubits. And if you have any n lattice sites, you have n qubits, then there are 2 to the n configurations. So this means that your state, and namely your physical properties, will be described in terms of a function of these 2 to the power n coefficients. And this automatically brings to bottlenecks in this problem. First is that the memory of your classical computer in which you're solving this problem has to grow exponentially with the lattice size, with the volume, or with the number of qubits. And also, since you will have, because you will have to store all these coefficients, and there are 2 to the n, so this is the exponential growth of the memory. Another thing is that you will have to do at least one computation for each of these coefficients. So the number of computations you will have to carry out will be also exponential in n. So that's very peculiar from quantum problems, that you have an exponential growth in memory with the system size and exponential growth in time. That's both. So you talk about, for example, people are talking about using quantum computers for optimization, classical optimization problems, traveling salesman kind of problems. In that case, the memory doesn't grow exponentially. You can store it in number of bits that is like proportional to the number of cities that you have in the problem. It's only the time that is exponential. But for quantum many-body problems, it's both. There is exponential in memory in time. In fact, you could try to trade one by the other. And so, for example, impose that your memory can only grow, let's say, linearly with the size of your system, or it's constant. For example, you say, well, I don't want to have a computer that is larger than the number of atoms that I have in the universe. That gives you an upper bound. And then you can say, what happens with the time? Well, then the time you have to pay a price. And so the time basically scales for typical problems like super exponentially. So it's not only an exponential, but to super exponential. So that's what's very peculiar of quantum many-body problems, this double kind of exponential dependence. And that's why, I mean, these problems are very difficult for classical computers, and more difficult, let's say, than these optimization problems, which are combinatorial problems. That's why from the field of quantum information, so many people have been thinking about solutions to this problem using the tools of quantum information. So one of the tools has been the development of some tensor networks. This provides efficient descriptions of the state. So you don't write these coefficients now like complex variables, that you write tensors in terms of tensors. And it turns out that for certain particular problems, namely you have ground state of local Hamiltonians, then the states that you will deal with will be in some corner of Hilbert space for which these tensor representations are very efficient and very economical. So they get rid of this exponential dependence in memory. And however, this only works for equilibrium problems and some kind of problems. Now, in general, the other solution is quantum simulation. Is something that many people realized many years ago, in particular Richard Feynman, that you better use a quantum system in order to simulate a quantum system, because right away you gain in memory. So you have n qubits and you want to simulate, or you want to compute properties with a qubit, just use the quantum computer, which is composed of qubits, instead of storing coefficients. Just prepare the state in your quantum computer, and now you want to measure, you want to predict any physical property, just measure, repeat, measure, compute the expectation value, and this will give the prediction of physical property. So that's what you gain right away in quantum computers, is in memory. And now in time, well, for certain problems you may gain, you can have that there is linear in time, the computational time, or it can be exponential, or it can be something else. And it depends on the problem that you're dealing with. And this, I will talk about that. So how different problems scale in time. Okay, so that's why I said at the beginning that probably for these first kind of devices, the quantum simulation problems are the most suitable, rather than classical optimization problem and many other problems that people are considering. And that's why many people are working on this quantum simulation with quantum computers. Okay, so now I mentioned two kinds of quantum computers, the digital ones. These are the ones that people like Google or IBM are constructing. And there are some other ones which are analog. And these are typically built in labs at different universities. In our Institut, Immanuel Bloch, for example, is building such analog quantum computers. And the idea is to take your favorite system, a set of trap ions. These are electrons in quantum dots, or atoms trapped in some kind of tweezers, or photons, or and so on. And then just make it in such a way that you can engineer the interactions among these systems in such a way that now the evolution of your simulator, it's or the description of your simulator is in terms, it's exactly the same, the Hamiltonian that you want to solve. So you engineer the interactions with the systems. You want to solve some Hamiltonian, then you engineer in such a way that you have that your system evolves according to this Hamiltonian, and in this way that you can do some predictions on your system. So here, I mean, like before, I mean, the fact that you use quantum states tells you that you don't have to store your coefficients, you just store the quantum states of your qubits, so you have this exponential gain in memory. However, as compared to the digital, well, and now as compared to the digital. So let me see some advantages and disadvantages. So imagine that your goal is to compute some dynamics. So somebody, I mean, here's a cartoon picture. You have a lattice. It could be something like that with some Hamiltonian, which is a sum of Hamiltonians. Let's assume that they are local. So for example, this could correspond to a discretization of a lattice gauge theory, where at the nodes you have fermionic degrees of freedom, and at the edge you have some spins or bosonic degrees of freedom. Hamiltonian, which is local, is acting maybe on plaquettes or crosses. Somebody gives you some simple initial state, so some product state, display 0, and asks you to compute the expectation value of some operator, some observable up to some precision epsilon. So how could you do that? Well, the idea would be to prepare in your quantum computer the initial state, then to evolve it according to this Hamiltonian, and at the end make this measurement, repeat it many times, and the number of measurements will just scale like 1 divided by the error square. That's because of the law of large numbers. And in fact, that's what you would do with an analog quantum simulator. However, with a digital quantum simulator, so how do you implement these dynamics? And that's not that simple. However, it's very well known. So in fact, Seth Lloyd was the first who proposed a quantum algorithm to use a digital quantum computer in order to implement these dynamics. So he says, well, if we want to compute this expectation value, let's prepare the state. So let's start with our initial state and then let's implement with the quantum computer in terms of gauge dynamics. And so what he had is that the computational time, now in the quantum computer, there is some overhead because it scales like the time that you want to simulate square, the number of qubits that you have square, and 1 divided by epsilon square. And the basic idea to get this algorithm is to use trotterization. So you say, well, let me just expand my Hamiltonian. It's a sum of Hamiltonians. Let me expand as products of small time steps. And then if the time step is very small, this is very close to the identity. And so basically these Hamiltonians will commute with, well, these operators, these unitary operators are close to identity. They basically commute with each other, so you can separate it. And then each of them is just a quantum gate because it's acting on few particles. So then at the end, what you will do is there's a set of quantum gates or 2 qubit gates or like that, one after each other. And the number of gates that you will have to produce will be proportional to this n squared, h squared, t squared. And this is in order to make sure that this trotterization error is small, that by trotterizing. And in fact, that's not, well, first of all, is that this grows like quadratically with n, and with a classical computer, the best that you can get is 2 to the n. And so that's why there is a quantum advantage in simulating the dynamics. In fact, since this paper, there have been many other papers in which this has been improved, not with trotterization, but with some other techniques. And now the best state-of-the-art algorithm scale, like n, like the one norm of the typical the operator norm of which of the local Hamiltonians is proportional to time, and in its case like the logarithm of 1 divided by the error. And as I mentioned before, this is for digital. You have an analog quantum computer, then you don't have to do anything, just let it evolve, and you will not have to trotterize anything. And that you see that this trotterization has so typically this algorithm, you cannot, I mean, in order to implement in a quantum computer, you need many gates. Let's say there is a lot of overhead in gates that you have to do that are not written here. And in this case, you see the overhead in the trotterization, which is this n square. So you see that in a digital quantum computer, then you will have to do many gates in order to simulate some time evolution. And that's a bottleneck for niche devices. So you ask Google to simulate some lattice gauge theory, the dynamics of a lattice gauge theory, or even some local Hamiltonian, then they will have to trotterize. Instead of doing some number of gates, they will have to do many more. And then since the error accumulate, then at the end, they will have a big error. So the result will not have so much to do with the result that should be expected. In this sense, I mean, dynamics is especially suited for quantum computers because of this exponential speed up, but it's not very natural for NISQ because you have to trotterize, and then there is a big overhead in gates in this trotterization, but this is straightforward for analog quantum computers. So then analog quantum computers would be more suitable for that task. Now, talking about analog versus digital.
Sorry.
Yeah.
May I ask a question about the previous slide?
Yes, of course.
So the Hamiltonian is clear, but can you say a little bit about what the Hilbert space is? So in the previous example, there was a qubit over each site.
Yeah.
This is the case over here as well, or is there just?
Well, that doesn't matter. So here the idea is that you have a finite dimensional Hilbert space on each lattice site, and maybe also in the vertices, which will double the number of lattice sites.
Okay, so there's a finite dimensional Hilbert space for green and orange.
Exactly. And you could think this is a generic problem. So I draw it like that to show that it can be general, but you could think of any problem that have only red let's say qubits, or both red and green qubits, and for both of them the same argument will apply, as long as you have finite dimensional Hilbert spaces. So here I'm considering that all Hilbert spaces are finite.
Okay, but okay, I thought you wanted to differentiate between the Hilbert spaces associated with blue, with green and orange in some way, but
no. It's just a drawing, because later on I'll talk a little bit about lattice gauge theories, and then I want to just
okay. So it's just okay. Thank you. Got it.
Okay, so what about advantages and disadvantages of analog versus digital quantum computers? Well, first, analog typically it's not universal, in the sense that the engineering that you can do in the lab cannot be arbitrary. You can engineer some parameters, and so you will be limited in the set of simulations that you can perform. On the other hand, a very big drawback is that there is no error correction, and we know that if we want to scale out our system, we will need some error correction. However, they're easier to build. Already there are quite a few simulators working in many labs. And another point is that they are more natural for simulating fermions. So you want to simulate a fermionic system with an analog simulator, just take fermionic components, just take electrons or take neutral atoms that are fermionic in character, and then you don't have any overhead. If you want to use a digital quantum computer, which is made of qubits, and you want to simulate fermions, then in principle you will have to use some Jordan-Wigner transformation, which will have string of operators and will give an extra overhead in the simulation. Okay, apart from that, there is something that is more subtle, but I don't know how to express it correctly mathematically, and I think that nobody has expressed it that mathematically. It's a kind of a feeling more than anything else, and it's how the errors accumulate. So typically, if you have an analog quantum simulator and you want to simulate this Hamiltonian, but you have some error. So this error, let's say that is some epsilon, some small parameter. Of course, there will be some error on each side. So this means that at the end, this operator that will appear here, the error operator, will be extensive, will be proportional to the number of sides. So this means that even for some given epsilon, if n is very large, the norm of this operator will be large. And therefore, any perturbative argument or anything else will not work. And in fact, you want to use this Hamiltonian to factorize numbers with any algorithm that you want, then you will get completely wrong, because this will change a qubit in the middle of the computation, and this error will propagate, and then the final result will have nothing to do with the ideal result. However, for quantum simulation, so you're not interested in, all the distribution, let's say the sampling, the final distribution or something like that. You're interested in some observables. You're interested typically even in intensive observable, energy per particle, magnetization per particle, some correlation functions. And so what you do is that you have to divide by n. And somehow the fact that you divide by n, it means that if you have 1 out of 10 qubits is wrong, then this means that you will have an error in your intensive quantity, which will be a 10%. And that's not bad for many problems that you want to solve in quantum simulation. And that's something that typically is not considered in computer science. So people don't ask this kind of questions. And I've been discussing with many people in computer science, Dori Taranov and Umesh Fazirani and these people, and ask them. And so they somehow it's difficult to understand for them. So what does it mean? And the way of understanding is just showing an experiment. This is a famous experiment where they observed with cold atoms in optical lattices transition from a multi-insulator and superfluid. So the idea is that what they did in the language that I'm using here is that they wanted to simulate certain Hamiltonian. And in this Hamiltonian, they changed the parameters, and they wanted to see that by changing the parameters, there is a phase transition. So all of a sudden, there is a very sudden change of the behavior of certain quantity. And that's what they observe. So they make some interferometry measurement, they change the parameters, it changes. So they already see, and they see what are the value of the parameters to observe that. Now you look at the experiment and you analyze what is the Hamiltonian that they had in this experiment. Actually, they had an error, and the error was huge. So it was something like a 10%, this epsilon. But still, they were able to observe very well the phase transitions. I mean, they characterized the phase transitions and everything else. And that's what I mean, that if you want to solve a problem in condensed matter physics and you want to know what is the phase that you have for some particular parameters, what are phase transitions. So maybe what is important is that this epsilon is small, but not that epsilon times n is small, because you're looking at intensive quantities. And that's another let's say, argument why quantum simulation is more robust, because the questions that you're asking are not so, let's say, so subtle like the ones that you ask typically in quantum computers. I mean, this is just an argument. It's not it's a qualitative argument. There is not a calculation behind. Of course, you can take some models and prove that you take Gaussian models that are exactly solved, and you can prove these sort of things. However, I mean, I cannot claim that this works in general. Okay, so what one reads from that is for quantum many-body problems, and especially analog quantum computers may provide useful information without error correction. And that's what we have at the moment. There are no error correction working. And so that's why the hope, that was I was saying at the beginning, that even with the current systems that we have at hand, it may still be able to solve some scientific problems that we cannot solve with classical computers. So as a final comment before just going into the algorithms, let me mention, so why do we want to do a quantum simulation? So some people will tell you, well, I want to solve some particular model. So Howard model, you know, that is connected to high TC superconductivity. And there are people who claim that you're able to somehow find the phase diagram of the Howard model, and it represents the one that is observed in high TC superconducting materials. Then you will have at least a microscopic model for some behavior, and then you can try to understand there what is going on. However, I mean, I wouldn't put all my bets into a couple of models that a quantum computer can solve, because it may happen that classical computers can solve them as well. In fact, you look at the Howard model, during the last 3-4 years, there was one Simon's collaboration, which have basically found the phase diagram. And so this may happen for some of the systems. So I don't think that this is not the most important application of a quantum simulator. However, it's better providing understanding. So you have a system that you can change and twiddle and change something, and to see how things change. And probably this allows you to have like a lab in your, that you're probing these many-body systems, that is like a Lego, that you can find pieces and then, I mean, maybe discover some new phenomena or try new things. Or more importantly, to benchmark theory. So we don't have many-body theories. There are very few many-body theories, especially for dynamics. And so it would be good to develop a theoretical results. And for that, sometimes you're a little bit blind. I don't know how is it in string theory, but I mean, probably you don't have experiments, and it makes things difficult. So if one had experiments, then one could probably, I mean, develop better theories for quantum many-body systems, better approximation methods, better even tensor network techniques. Okay, still, I mean, there are many challenges. Of course, there are experimental and technological challenges. Still, I mean, state of the art is not at the level in which we can just start just solving problem and benchmarking methods. New algorithms, I mean, are probably required, and I'll talk a little bit about that. And also it would be interesting, and it's still happening, that some industries are also showing some interest for this kind of analog quantum simulators and quantum simulation, because they realize that for some of the materials that they are designing, especially in semiconductors, physics, or when they took it about these very small chips and so on, then this could give some input to what they do. Anyway, so this gives you a kind of a very, very long and broad introduction for the motivation and what is the setup. At least, I mean, some of things are clear, some of them are opinions. But anyway, so now I go a little bit to the meat of the talk. And so I want to talk now about quantum algorithms, and especially for zero temperature and finite temperature systems. And that's something that we have been working lately, and then some applications in the field. And again, so this is, I mean, you can imagine that you have any lattice. This is just an example of a possible lattice, but could be any lattice only with red points. And this could be qubits, could be fermions maybe, or it could be qubits or any other system. What I will, I mean, considering the following is that my Hamiltonian is local. So it's not, I mean, many of the things apply to non-local Hamiltonians, but let me assume, just to make things simpler, that this Hamiltonian is local. And by local, I mean that the Hamiltonian can be written as a sum of terms, and each of the terms acts on some bounded region, like the ones that is represented here. Okay. And so the first thing that I want to talk about is quantum algorithms for zero temperature. And so let me formulate the problem a little bit more precisely. So I am giving a lattice with n lattices. I'm giving a Hamiltonian, and with in terms of these other small Hamiltonians, which are local. And this is an operator. In principle, I could compute what is the spectrum, the eigenstates and eigenvalues, and I will have here the spectrum. And so what I'm interested is in the property of the ground state. So the eigenstate corresponding to the lowest eigenvalue. And the problem is like before. So somebody gives me an observable apart from the Hamiltonian, tells me, and my goal is to compute this expectation value up to certain accuracy. And now I want to grow my system and want to see if I have more bigger and bigger systems. So if I grow n, how the computational time will grow with n and also with the error. So that's the typical question that you ask in this case. Okay, so ground state properties, and you want to see how the difficulty, the computational time grows with your system side. And it turns out that that's a very difficult problem. So already many years ago, it was shown by some people that this is a so-called QMA hard problem. I mean, you have to specify it more precisely. You have to specify as a decision problem, but basically what it says is that if you're able to solve this problem, then you would be able to solve many problems that we believe that not even a quantum computer can solve efficiently. And so the QMA is the class of problems that a quantum computer can check efficiently, but cannot compute efficiently. So it's like the counterpart of NP, complexity class. Okay, so this problem, as I mentioned here, is in QMA. So probably the computational time would be exponential with n. And indeed, if not, this would be really a very big surprise. And so, in fact, now what matters here is what would be this alpha. If alpha was, I mean, 10 to the minus 5, then the fact that this exponential wouldn't matter so much. If alpha is 100, then this would mean that basically we cannot do anything. So that's why, I mean, there have been many algorithms now trying to find how much is the alpha. And well, in particular, this is not as bad, because it turns out that now if you would compare with a classical algorithm in which you have the same restrictions in memory, as I mentioned before, you want to trade time by memory, then this will scale like 2 to the n to the power n. Okay, so that's still an advantage with respect to a classical computer, just because of the memory side you want. And in terms of what is this alpha, well, it depends. So, I mean, some time ago we wrote a paper, and this has been improving in the meantime, that is basically, it depends on the gap between the ground state and the first excited state. And it scales like 2 to the n halves divided by the gap. And with the error, it scales like logarithm 1 over epsilon. But this may change. So there might be somebody who comes with a better algorithm, which is n over 3, but that's current state of the art. So I'm not going to talk about this algorithm. But let me also mention that this algorithm, in order to get the scaling, it requires the combination of many techniques. So amplitude amplification, kind of put Grover's algorithm, many algorithms in place. So this will not work for niche devices. That's why people have been interested lately in some heuristic algorithms. So these are algorithms that would also solve the problem, would compute the properties of your ground state. However, you cannot prove what is the computational time. So you don't know. And sometimes they may work and sometimes they may not work. And so one of them is the adiabatic algorithm. And of course, it's something that is known for many years. So here's the paper where they propose it for optimization problems, but you can use it for preparation of ground state. So the basic idea is that if you have the problem Hamiltonian, what you can do is to consider some other Hamiltonian which is trivial, for example, in which the qubits don't interact, and for which the ground state is just all the qubits are in 0. And now you can deform continuously one Hamiltonian into the other one. And if you compute now the eigenvalues, and there is no crossing, so the ground state energy does not cross with any other of the excited states, then if you change, you start with your initial state in the state 0 and change the parameters the deformation of your Hamiltonian sufficiently slowly, then you will land in the state psi0. It's a way of preparing the ground state. And what can compute, so what is the computational time? And the computational time, so typically, I mean, scales with the inverse gap. And so that's good, because if you consider an arbitrary Hamiltonian, the inverse gap typically scales exponentially down with the system size. However, in physics, for most of the problems that we have, the Hamiltonians just scales like 1 divided by polynomial of n. So you take any system that is translational invariant, and then you go to a critical point where the gap will close. It will close like 1 over n or 1 over n squared. So this means that this algorithm, if it was the case, then it would be polynomial. So we would prepare the ground state in polynomial time. However, I mean, if somebody is given a problem, it's very difficult to compute what is the gap and to prove that it scales in one way or another. So that's why this is called a heuristic algorithm, in which you try it, and if it works, it works, and if it doesn't, it doesn't. Another kind of algorithms that people have been considering are variational quantum algorithms. They are very popular now. And the idea is that you start with the ground state, and then you take some quantum gates that you parameterize with certain parameters, and you just fix the number of gates and where they are acting, but you don't fix the angles of the gates. And so what you do is minimize the energy with respect to these parameters, like in a variational principle. And if you chose well the gates, then you may get a good approximation to the ground state, like we get with variational problems. These, however, I have to say that, I mean, they're very popular, but somehow they have many drawbacks. So for example, there's a nonlinear optimization problem. So they get stuck in local minima, and there's in the noises. So I'm not so keen on variational algorithms, at least for the moment. So something that you can do is that you can combine the two ideas, and that's something that we have recently done. And the idea is to now to run a variational algorithm, but to run at different speeds. So maybe at the beginning fast, then slow, then fast, then slow, then fast. So you fix the total time, and then you divide it in intervals. And what you do is that use the variational principle to choose what are these intervals, the length of these intervals. And so it turns out that in this way you can speed up the variational algorithm. So I want to tell you more on that. But for example, we tried, I mean, this model, that's a typical non-integrable model in one dimension that we can solve with other methods, with tensor network methods. So we can really simulate the simulator with this classically. And in this case, we can make predictions of how this algorithm will run with respect to the adiabatic algorithm. And so what we see is typically in time, this is the computational time for 53 qubits, we say a 10-fold speed up of the algorithm. And a 10-fold speed up, this may be useful because exactly in these NICS devices or in the analog quantum simulators, you wouldn't like to wait for a long time because the errors will accumulate. And so speeding up these systems are interesting. So maybe another, just to mention something about these adiabatic algorithms. So people have been proving, so what are computational times for the adiabatic algorithm in terms of the gap, or a lower bound on the gap, in terms of n and in terms of the errors. And so that's, let's say the standard result is that the computational time for the adiabatic algorithm, if you have a lower bound to your gap delta, that scales like you have a local Hamiltonian, scales like it's proportional to n, inversely proportional to the gap, to the third power. So what we showed some time ago is that you can improve this a lot. And in fact, you can get for local problems, you can get scaling which is polylog in n. So it's like a log square of n or something like that. And the way of doing that is very logical. So let's explain you what is the idea. The idea is that you showed that the adiabatic algorithm, in which you change all your Hamiltonian, you deform it slowly. You could also do it just first changing the first term in your Hamiltonian, then the second, then the third, then the fourth, so sequentially. And then you show that the time, then so you have to change n terms, like the n terms that compose your Hamiltonian, then it will be proportional to n. So there is no gain with respect to this other algorithm. Still proportional to n. You just change the first Hamiltonian, then the second, then the third, until you deform all of them. However, you realize that if you change the first Hamiltonian, then because of the Lieb-Robinson bound, you will only affect the qubits that are around it. So this means that you can parallelize. So you could take another Hamiltonian, which is far away and changing at the same time, and another one which is far away changing at the same time. So this means that you can change many Hamiltonians at the same time, and things will not change. And so you can change, since the Lieb-Robinson bound, I mean, in order to make sure that you have some error and so on, will have some log n dependence, and you can change n divided by log n, basically, terms at the same time, and therefore the circuit depth, so the number of changes that you will have to do would be log n, and this is how you get basically this number here. Okay, so far this was about finite energies and finite temperature. So I want to now move on to, for zero temperature. So I want to move on now to finite temperature and tell you a little bit about algorithms at finite temperatures. And so the idea is that you now have a mixed state. You have a Gibbs state, for example. You would like to compute. So you have a Gibbs state. You would like to compute the expectation value of some observable with a Gibbs state at certain temperature. Or maybe another problem is microcanonical. So somebody gives you some energy, and then you would like to compute the expectation values of observables with the state which have more or less this energy, maybe with some uncertainty delta, with some small uncertainty, because the spectrum is discrete. So it may happen that you don't have even an eigenstate at this precise energy. Well, it turns out that this problem with a quantum computer has to be QMA hard as well, has to be difficult. And the reason is because they include the zero temperature. So the energy that I give you is this one here. I'm back to the zero energy. If I put T equals 0, then I'm back to the zero energy. So this is a difficult problem. However, we also know that if T goes to infinite, if T is very large, then it's a trivial problem. So in the middle of the spectrum, the states have all observables trivial. So what happens classically is that there is a temperature or some energy in which the problem changes from something that is easy, high temperature, to something that is difficult, that is low temperature. And for quantum computers, then something similar will happen. So there will be a phase transition in complexity from something that is difficult at zero energy to something that is simple. And so one could expect is that this transition occurs at different points. So there will be a window in which a quantum computer would be more efficient than a classical computer. And so we want to get arguments so that this will be like that, and to find algorithms that would try to find this window or that will work in that window. And so I want to talk about a couple of them very briefly. And okay, so let me formulate the problem. And so the problem is first the microcanonical, and that's because I give you some energy, and I would like to compute properties of this energy. But as I mentioned before, you have to formulate it properly mathematically, because that might be not an eigenstate at this particular energy, because you have a finite system. So the problem, a little bit more precise, but not completely precise, is, and you want to see also how things scale. So you want to grow the system. So you have to have a way of defining the growth. So the idea is to fix the energy density. And now for some given size, then you compute m times c. So this is the energy. And then what you would like to do is to take an observable O and compute the expectation value with a state which has this mean energy and a variance which is delta, which is also a given parameter. So again, you're giving the energy density, you're giving the observable, you're giving this variant delta, you're giving an error epsilon, and then you would like to know how does the computational time scales with n, with epsilon, and with delta. Just to keep in mind, so what is relevant, what delta is relevant. Of course, if I choose delta very large, then I will not get any interesting result, because I can use any state that I want basically with that energy. And so it turns out that now you can look at kind of ETH thermalization hypothesis and so on. And then you can see that for relevant problems, you will have to scale this delta as 1 over n. So in the following, this is what I want to consider: problems of this size in which this delta scales like 1 over n. Okay, so the first thing is that these problems with classical computers are difficult. And the main reason why they're difficult, so you can try to solve this problem with, for example, tensor network methods. Okay, so what you would like to do is to prepare a state that has this energy and this variance. But you can easily prove, actually, this was shown in this paper, that if you reduce the variance, then you have to grow the entanglement of the state. Okay, so you make it smaller, and the entanglement of state grows somehow like the inverse of the variance. And we know that the kind of bond dimensions, so the number of parameters that we need in the tensor network grow exponentially with entanglement. So this means that this will scale like the exponential of 1 over delta, the computational time, which is the number of parameters that you have to optimize with tensor network methods. And so if delta is 1 over n, this is exponentially in n. So you see that for this problem, then you have an exponential problem. And this is like everything. So maybe there is another algorithm that works better classically, but we don't know, or at least I don't know. And so this is why it's a good to try with a quantum computer. And let me tell you one quantum algorithm that would work for that. And so the idea is very qualitative, what I present here. So the idea is that first, imagine that you can prepare a state with this energy. For example, a product state, okay, a trivial state. You prepare a product state, and then you find one that has this energy. And of course, this state will have the right energy, but doesn't have the right variance. And in fact, this state, if I would measure some observable, would be completely trivial. There would be no correlation because this is a product state. So the next goal is to make it thinner, so to lower the variance. So in the second step, what you will do is to apply the quantum computer will create a spectral filter, which will filter the energies and will make it narrower. And once what you have it narrower, then you will have a state that is narrow, so you could do the measurement. However, it turns out that if you want to implement this algorithm with niche devices, then this algorithm to make it narrow requires many, many gates. So instead of that, you use a trick, which is called time series. And this time series, which tells you that, well, at the end, I don't want to have the state. What I want to do is to compute some expectation value with that state. So what I do is that to express the expectation value in terms of some quantities, and these quantities are the ones that I measure with the quantum computer. So let me be a little bit more specific on these topics. So the first is that I told you, okay, so you prepare a state, a product state, easy to prepare state with this energy. Of course, if I give you some energy that is very low, there is no product state that has energy. And in fact, I mean, it has to be something like that, because I told you that, I mean, this is a QMA hard problem. So if your energy is very low, you will not be able to prepare, I mean, to solve this problem. So this indeed is a restriction, but this is a necessary restriction that we must have, because we know that otherwise we would be able to go all the way to the ground state, and this is a hard problem. However, this restriction, I mean, one can argue. And so what you can say, well, with a product state, maybe I cannot go very low in energy, but you can show that you can go extensively low with energy. So maybe you can go to half of the spectrum, let's say from to half between the center of the spectrum and the minimum to half of it. What you can do is that you can take now blocks, like say 2 qubits, and prepare product states of blocks. And then you will be able to decrease the energy a little bit. And then you can show that if you do that, and then you take blocks that are log n, then you will be able to get very close actually to the ground state. And this will give you still a polynomial time algorithm, because you have only log n, let's say, qubits in a block. So the Hilbert space dimension of this block is still polynomial in n, 2 to the log n, which is polynomial in n. So therefore, you will be able to prepare this state efficiently and so on. And therefore, this tells you that indeed you will be able to get very low in energies with this method. So it's a restriction, but actually if you scale it, that's not such a bad restriction. Second, the spectrum.
Sorry to interrupt. Are you considering a one-dimensional system or?
No. This is in any dimensions. In any dimensions.
Okay.
In any dimension. So you could block now. For example, you have 2-dimensional lattice. You block 4 spins and prepare a product state of 4 spins times 4 spins, 4 spins, 4 spins, and of course the product state will have lower energy than the product state of single spins, because you have more degrees of freedom. And so you can make the blocks bigger, and then you do the sum scalings, and then usually it can get very low, still with polynomial effort. Now, the second idea is the spectral filter. And the idea is that if you have the product state, what you would like to apply is something like a Gaussian operator. You see, it's an operator in which the Hamiltonian filters energies that are delta away from the center. That's what you wanted to have. So you would like to apply this operator to that state. Of course, this operator is not unitary. So then you cannot apply with a quantum computer. However, what you can do is a kind of Fourier transform of this operator, and then a discrete Fourier transform. And so you can express this operator as a sum of operators that look like generator of evolution, so evolution operator, e to the minus IHTM. And so that's the second trick. Okay, you apply this filter, but you will apply like a linear superposition of time evolutions. So you would like to prepare this state with a quantum computer, what you would like to do is to prepare certain linear combinations in which your state has evolved with some time, plus another state that has evolved at a different time with different coefficients. But that's what I told you before, that it's very difficult to prepare with a quantum computer, with the NIST devices at least. So that's why you have the next step. And the next step is that since at the end you want to measure some observable with this state, then you can replace it in this formula. And if you replace it in this formula, you can see that you can re-express this observable in terms of these parameters, this A of t and B of t. So you see what you have to do is to measure kind of Loch-Schmidt echo. Start with the product state, evolve for a time, and see what is the amplitude of landing in the same state. And so this is what you do with a quantum computer. So with a quantum computer, you start with a product state, this product state here, you evolve for a time, and then you see if you are in the same product state. So in principle, you could measure yes, each of the qubit if it's in the product state, and this will give you the absolute value of A squared. Now you will have to extract the phase, and then there are ways of extracting the phase. So in many problems, you can even extract it classically. You can compute classically this phase, and in this way, you can run this algorithm. And now what you can do is the computation of the gates that you need for doing that, what I told you before. And now if you do, then you see that the computational time is case polynomially with 1 over delta. So you see that there is a quantum advantage. There is an exponential speed up with respect to the classical algorithm, because it doesn't scale like exponential of 1 over delta, it scales like 1 over delta. And it's very simple. I mean, you do back of the envelope calculations with the spectral functions, you will see that it's something that has to come out, something like that. Okay, so that's an algorithm, a quantum algorithm, let's say for kind of microcanonical problems that has an exponential advantage that doesn't work, a proven exponential advantage, let's say it doesn't work for all energies, has restrictions in the energies, right? But for the energies for which work, this has this advantage. Now, what about finite temperature? There is another algorithm. So now you can use the same ideas to compute things at finite temperatures. And the idea here is that, well, the problem is the same. So you're given some temperature, you're giving some observable, you're giving some precision, and then you want to see how the computational time scale with n, epsilon, and t. And so this is something for which, for some cases, you can use quantum Monte Carlo. That's a method that people use in condensed matter physics and high energy physics. However, this quantum Monte Carlo has a sign problem for certain problems where you have fermions and some particular cases. And so it turns out that what you do is to apply the same ideas that I told you before for this algorithm. And you can take, and I don't have time to explain it, but what you can do is to, I mean, basically use the classical quantum Monte Carlo. We use ample configurations, but now the sign problem happens. What occurs is that you cannot compute what is the probability of some configuration. That's where you don't, where you have the sign problem in classical Monte Carlo. So you can use the algorithm that I told you before to compute the classical probability, avoiding the sign problem. So with this algorithm, it's based on a classical Monte Carlo in which the quantum computer is used as a subroutine, which computes probabilities. You sample classically, but you compute probabilities quantum, and in this way, this circumvents the sign problem. That's a heuristic algorithm, but it's a way. So this means that, I mean, I think that it will have utility because it will, I mean, avoid the sign, circumvent the sign problem, combined now with a classical computer with classical Monte Carlo. Anyway, so I think that I'm almost finished. So let me just move very fast to now some particular problems. So what are problems that you can address with analog quantum computers? So I mentioned that problems in condensed matter physics, high energy physics, and quantum chemistry. And indeed, with these analog quantum simulators, so people, and in particular in our group, we have been thinking about how you could solve particular problems in these three fields now with these analog quantum simulators. And I want to say a couple of words for each of them. So for condensed matter problems, in condensed matter problems, the kind of the toy model, or the model that people work, is called Hubbard model, in which is composed of fermionic degrees of freedom. So these are fermions that hop from one lattice side to another lattice side. And the way of doing that with an analog simulator is to build a system in which you have atoms that are fermions, for example, and that hop from lattice side to lattice side. And these are atoms in optical lattices. And this is why with atoms in optical lattices, people are trying to solve condensed matter physics problems like Hubbard models. Now, what about lattice gauge theories? Well, if you want to simulate relativistic theories, then because you will have to deal with matter and gauge fields. So you have to have relativistic physics. So that's typically very different from these atoms, which are move at very low speeds. The model has to be gauge invariant. So there are many constraints that your theory has to have. And in fact, I mean, it's useful, at least for the experimentalists, to work with a Hamiltonian formulation, but it turns out that this is very well known. So for atoms in optical lattices, the fact that you have to work with matter and gauge fields means that you will have to combine bosonic and fermionic atoms. So the bosonic atoms will represent the bosonic degrees of freedom, the gauge field degrees of freedom, and the fermions, the matter. The fact that this relativistic doesn't mean that your atoms will have to move at relativistic speeds, because we know that if we put them on a lattice, then you have relativistic dynamics. You have a dispersion relation on a lattice, like a sine. There is some part where it's linear, and so you have to work close to that energy, and then you will have a linear dispersion relation, so you have a relativistic theory. That is gauge invariant. Actually, it turns out that these atoms, when they interact with each other, has some conservation law. So for example, the total spin or total angular momentum is conserved. And so what you can do is to transform in this tailoring that you're doing in transforming one problem into the other one, you can transform this local this local conservation property into the gauge symmetry that your lattice gauge theory has to have. And Hamiltonian formulation, well, this was done already many years ago by Kogut and Saskin. So what we can do is just take a model in lattice gauge theory, write a Hamiltonian, Kogut and Saskin, and it would look very much like the kind of Hamiltonians that I was talking about. And this is why the algorithms that I told you before can be directly used with quantum computers, with analog quantum simulators. What about digital quantum simulators? Well, I mean, maybe to mention that the main difficulty, experimental difficulty, is if you go to 2+1 dimensions, because these models have plaquette interactions corresponding to magnetic field energies. And this requires a forward interaction. However, in atoms, the natural thing is that they have two-body interactions. So you have to engineer out of two-body interactions, forward interactions. And the way of doing that is by perturbation theory. So you have to go to fourth order perturbation theory. And that's very delicate. So I think that no experimentalists want to work with terms that are fourth order in perturbation theory. So that's why it's very difficult, and there are no experiments, and this is really what is difficult. But anyway, let me go to a problem, which is, what about the fermions for analog simulators? Well, it turns out that, with Frank Fistrate, we wrote many years ago a paper in which we showed that fermionic models can be mapped into local fermionic models, can be mapped into local bosonic models, just by adding some ancillary fermions. And so what we showed is actually the lattice gauge theory, you can do the same thing, but it's even more natural. So in other words, there exists a unitary transformation in your system such that transforms your Hamiltonian, which has fermion and gauge fields, into a boson and gauge fields. And so you have to put ancillas. So, you put some ancillas, you put this unitary transformation. This unitary transformation is local. So this means that at the end, you want to solve a fermionic problem in lattice gauge theories. Actually, I can give you a Hamiltonian, which is local, and it contains only bosonic degrees of freedom. And so you have to solve a bosonic degrees of freedom, and therefore you could use them in a quantum computer. So that means that even digital quantum computers, fermionic problems shouldn't be a problem. And in particular, this is because you have local interactions. So at the end, you will have to add a couple of ancillas, and then there is some gauge fields that appear, so a new symmetries that appear and so on. But at the end, the claim is that you have a bosonic Hamiltonian. Okay, and now to finish now with chemistry, what about chemistry? What in chemistry, so typical problem is that you have you do Born-Oppenheimer approximation, where you fix the position of the nuclei, and then you like to find what is the electronic configuration that minimizes the energy. Then you compute the energy for the position, and then you would like to change the position of the nucleus, which is like an infinite mass. And then in this way, you will have the energy curve, the dissociation curve. And if you have this dissociation curve, then you can see, for example, where are the equilibrium position, and so what it will be the configuration of your molecule, which is a typical problem in chemistry. So the problem, or at least one of the problems, reduces to solving a problem in which you have fixed position in the nucleus, and you have just electrons that are interacting with the nuclei and among themselves. And so we had a paper a couple of years ago, or a couple of years ago, in which you showed that you could do that with atoms in optical lattices. And the main problem there is how to simulate the interaction between two atoms that are neutral that give rise to a Coulomb interaction. So if they're neutral, how could they have Coulomb interaction? And so what we did is that we simulated nature. So you write QED and you have electrons, then there will be a coupled to the gauge field, and the gauge field mediates interaction. So you eliminate this degree of freedom, then you will get Coulomb interaction. And so you can do the same thing. You can put a bosonic degree of freedom, bosonic atom that interacts with both of them with local interactions. And this, it turns out, that gives rise to some effective Coulomb interaction. And so we propose to do simulations with these systems. So, okay, altogether this finishes the talk. So I was talking about quantum simulations, and so how to solve many body problems with quantum computers and analog simulators. I was mentioning that probably this is the most natural application of quantum computers, that analog simulators have certain advantages with respect to digital simulators. The motivation maybe is more benchmarking than anything else, not to maybe solve many problems, but that to have a way to check theories with that. But there's still many challenges, but I mean, we hope that in experiments like the one that we have in our institute, then people will be able to do something like that. And so here, a picture of my department, the theory department in our institute, and these are the people who were involved. So in particular with these algorithms that I was mentioning of finite temperature, Maricar Manuel, Cyril, and Benjamin Schiffer. These are people with whom I collaborated in the past, and they are now in some other positions. They were, most of them, postdocs or PhD students in our group, and these are some external collaborations. And with that, I'd like to thank you for your attention.
Well, thank you very much. I guess we'll have some time for questions. So I open the floor for questions. I have a question about the bosonization. So you said you could write these fermions in terms of bosons. Can you express this operation that you did? Well, first of all, is in how many dimensions were you doing this?
In any dimension.
Yeah.
In so one dimension is trivial with Jordan-Wigner transformation.
Sure, yeah.
But so you can do it in higher dimensions.
Right. So I was wondering whether one can express this operation you are doing in the continuum and as a continuum field theory, that you start with the field theory of fermions and then you do something. And
I think that we cannot take the continuum limit here easily and express it as a quantum field theory. Mm-hmm. And the reason is because, you see, there are, I mean, the fermionic degrees of freedom appears now when you use the Gauss law in order to eliminate the fermions. And so it will appear some phases like e to the I electric fields. Mm-hmm. And this is a kind of very discontinuous function. And so I'm not sure how to take the continuum limit there. I mean, what I think is that, of course, you could take you can do renormalization and go to the continuum, like with typical renormalization arguments. However, to take the limit of this Hamiltonian and to have some quantum field theory, some action or something, I'm not sure I know how to do that, or if this can be done.
Mm-hmm. Okay.
I had a naive question about the definition of errors occurring in the Hamiltonian that you define. So the errors were defined as a sum of Hn plus epsilon sum Vn. Can the errors be completely localized in the sense that all the Vn's are 0 except 1, so that all the errors basically occur in a single face or a plaquette?
Right, they will be local. So this, and at least in the experiments with cold atoms, these are neutral atoms, so there are no interactions that are long range. Mm-hmm. And so what happens is that you will have some lasers and something, and then the laser may not be perfect, may have, maybe it doesn't have the intensity it should have, or doesn't have the frequency that it should have. And therefore, at the end, you don't get the Hamiltonian that you want to have. But at the end, all those, if you see what they are single body interaction, single body terms that you will have, even the correction. So this will be local. Mm-hmm. And there could be some errors also because of interaction. So which are a little bit non-local. These atoms, maybe they interact through van der Waals interactions with each other. Mm-hmm. But these van der Waals interactions decay very, very fast, like 1/R6. So this means that even these errors produced by interactions will be local. Will be kind of local.
Right. Cool, thanks. And so this is I guess a kind of a fantasy question. Is it possible to simulate Cooper pairs in a superconductor by using quantum computers?
Yes.
So your Hamiltonian would be the Schrodinger operator. Your lattice would be basically the Bravais lattice of some crystal. And you're looking at dynamics of two electrons. And at very low temperature, they should form these these amazing things called Cooper pairs. But
I mean, you can. This is, I mean, relatively simple. So you just take the Hamiltonian, which is the Hubbard Hamiltonian with negative interaction. You cool it down, and then we know that these Hamiltonians will have Cooper pairs. Mm-hmm. And so you will have Cooper pairs, and the elementary excitations that you have there are excitations of these Cooper pairs. And so you will see the dynamics of these Cooper pairs there in your system. So indeed, yes, so you just have to tune the parameters in such a way that you have a Hubbard kind of Hamiltonian. So you'll have to have spin 1/2 particles. Your atoms should have a spin 1/2 particles, and they have attractive local interactions. This is the Hubbard model. And if you have something like that, then at low temperatures, this is well understood, and you will have the physics of Cooper pairs. The difficult part is positive interactions. When they are a repulsive interaction is where the Hubbard model, we don't know how to solve it.
Thank you. That's really nice.
At the beginning of your talk, you mentioned that a quantum simulator, you'd engineer the Hamiltonian, but you wouldn't quite have the right Hamiltonian. And that would produce some kind of errors. And then you remarked that computer scientists have trouble saying anything about how big are the errors in the simulation resulting from the error in the Hamiltonian. It sounds like asking them to explain that in the abstract is a lot like asking them to understand the renormalization group in general, because the way a physicist would analyze it would be by some knowledge of the believed expected infrared behavior of the system you're trying to simulate, and then try to analyze how sensitive the physics is to a microscopic change in the Hamiltonian.
Yes, yeah. So probably, I mean, you're taking a limit that I was not taking here. You want to take a limit, the thermodynamic limit, and compute now quantities in the thermodynamic limit. That's another question that computer scientists don't like, namely that you ask something that is not how something scales with n, but you ask the limit n going to infinite, and therefore you could see how the error in this thermodynamic limit would scale. And indeed, I think that that's exactly what happens. So when I was talking about intensive quantities, they will converge in the thermodynamic limit to something, and you would like to know how this converges. And then you would like to know whether the perturbations that you have are relevant or not relevant, for you would do renormalization, and this renormalization will converge or not. So yes, indeed, I think that you're right. Yeah.
Can you say again quickly what the issue was again with the plaquettes? If you wanted to simulate lattice gauge theory like this, you could do a triangular lattice. You don't have to do a square lattice, so you could have 3 things rather than 4 things. But is there really such a huge qualitative jump between nearest neighbor and something that even just involves 3 guys?
Yes, for these atomic systems, it is. So you kind of start with, I mean, it's not first principle, but let's say with kind of atomic physics Hamiltonian, and you derive everything. You will see that the Hamiltonian that the atoms fulfill contains 2-body interactions, and so this means that you have, a sum of pairs of operators that are acting, and then the Hamiltonian you want to simulate has 3. So how can you get from operators that appear only pairs to something that has 3 operators? Because this, the magnetic field is a cosine or something like that, and has inside the sum of the terms in there. And so how do you do that? And you cannot do it. The only way of doing something like that, or one way of doing it actually, would be to do perturbation theory. So to see, okay, so let's get a low energy behavior in such a way that the effective Hamiltonian will have these 3 or 4 body interactions. And so this means that they will have to decrease even more the temperature to go to very low energies, and the parameters will get smaller. And that's an issue for them to get to very low temperatures. And that's why it gets more and more difficult the more body interactions they have. And that's why actually for lattice gauge theories, that's a problem, that because you have these kind of 4 body interactions in all these models in dimensions higher than 1 + 1. In dimension 1 + 1, you don't have them because they're not magnetic fields, and then it's relatively trivial. However, in condensed matter physics models, they don't have. So typically models, Hubbard models and things like that, there are 2 body interactions. So this is why it's very natural.
You were talking about taking some blocks at some point of a certain size and doing a product state as an approximation to the. Is the idea that the size of the block has to be the size of the inverse temperature, and then you essentially will have a product state would be a good approximation? I'm just trying to understand where the intuition was coming.
Well, okay, so let's say the intuition is basically that imagine that I give you some Hamiltonian and I ask you to find the ground state, and then I take big blocks and I minimize the energy in each of the blocks. Mm-hmm. Then I will make an error which will be surface, mm-hmm. whereas my energy will be bulk.
Okay.
So you see that the error is surface with respect to bulk. Mm-hmm. So you will increase, then you will decrease the relative error. That's the idea.
Okay.
So in your microcanonical discussion, did you use the fact that you have a gap near there, or is that not relevant?
That's not relevant because I'm talking about the middle of the spectrum, or let's say not all the way to the ground state. So there, typical what happens, and that helps a lot, let's say, is that, or makes it more difficult actually, is that in these local models, the density of states, it's kind of a Gaussian. So it's center, very much at the center, and then there has these tails. And this is why when I ask you about properties in some energy, then you have a tail of a Gaussian. So there are very few states there, and that's why it's very hard to get them. And this is what it makes it very difficult. This is like a nozzle, like a bottleneck that people have. And that's what is you can imagine that you have like many states in the center of the spectrum. You have to go to one that is just down there. You start moving. So it's very difficult just to get in the direction down in energy where you will move around. And that's what makes things difficult if you go to lower and lower energies. But of course, now, if we talk about 0 temperature, then the gap is important. And so then there are some results that people will believe. And so people will say that, okay, so if I have a gap, then in principle, the adiabatic algorithm should help me to get there efficiently. Because probably I can connect this state adiabatically with some other state that is trivial, that doesn't have interactions, without closing the gap. And if I'm able to do that, if there is no phase transition, or even if there is a phase transition, but the scaling of the phase transition, as I told you, the gap only decreases like 1 divided by n or 1 divided by n squared, then the adiabatic algorithm will work. So in fact, for these explanations that I was giving you, if you want to find the ground state in practice, probably this will work well because of the existence of these gaps and the scalings of the gaps that we know from some models that we can solve. Now, for the macrocanonical ensemble and canonical ensembles, if I was going to energies that were well above the gap, then it doesn't matter whether there is a gap or not.
Yeah, but then how do you get accurate? How do you know how do you control your accuracy when you don't have a gap? That's my question.
Oh, because you're promised that you will have the right state. So the algorithm tells you that if you do some specific time steps and then you measure and you didn't have errors in your quantum computer, then for sure you will get the expectation value of an observable at this temperature, at this energy. That takes care of the algorithm. I mean, that's
yeah, thank you.
So in this discussion of the energy eigenstates, you were doing evolution backwards and forwards in time, right? If I understood correctly or not? Because you said it was like a logarithmic echo.
Oh, I see. Yeah, well, no, what I was doing is starting with a product state, evolving, and then checking if I am in the same state.
Ah, okay, fine.
That's a logarithmic echo. I mean, the probability that you end up in the original state. So the idea is that you would prepare. I mean, the algorithm. What it does is that you prepare a product state, then you evolve it, and then you measure your qubits.
Okay,
and then
fine,
you check that they're in the same product state.
Okay. Okay, well, if there are no more questions, I guess we thank you again and for a wonderful and very interesting talk. And I guess we'll see you for more discussion later.